Thanks for the introduction. So my name is Georgios. I work at Lawrence Livermore. I'm going to talk to you about programming GPUs with OpenMP and Python. The system that we built, the compiler, is called PyOMP. I want to mention my co-authors and collaborators. So Todd Anderson from Bodo, Stuart Archibald from Anaconda, Bronis from the lab as well, and Tim Hudson from mostly Medley and retired. So the motivation is that we want to have portable, productive, and high-performance parallel programming in Python. And the building blocks are there. We have OpenMP. OpenMP is easy to use. It's portable. It's popular. I don't think anyone's going to disagree with that here. Then we have Python, and Python is easy to use. It's a high productivity programming language. It's very popular. In the keynote, it's consistently first in the TIOB index, but it has the issue that it has very fragmented parallel programming support. And then the other key ingredient of creating PyOMP is Numba. And Numba is a just-in-time, fast, easy-to-use compiler for Python that uses LLVM. So basically, PyOMP, that's the no-brainer. It takes all those things, puts them together, and what it gives you is the capability to do OpenMP programming, OpenMP parallel programming in Python, compiled through Numba so that you can get high performance. So there are other approaches for doing GPU programming in Python. You can use one of the high-level libraries like Copy, PyTorch, TensorFlow. They give you APIs for operations, element-wise operations, or linear algebra operations to run the GPU. There's also a very nice effort to port Cocos to Python. So it supports one or two of the parallelism abstractions of Cocos that is called PyCocos. And then there is also data flow languages like DACE and TaiChi. You can describe your program in a data flow DSL, and they can basically execute on the GPU. So all those are nice. They're very good. Some of them are very robust and they work very well. But the problem is that they all lack the generality of OpenMP. If you have a custom algorithm that you want to parallelize, you're going to find troubles, one way or another. So OpenMP, we have a lot of experience. We know it works. So why not, use it in Python? This is to give you an idea of a little bit, what it looks like if you write a program in PyOMP, OpenMP in Python. And this comes from the CPU world. So, I'm starting there because that was like the first instantiation of PyOMP. It was easier to implement. So this is a very basic hello world program in PyOMP. You have your imports. So your imports from the Numba OpenMP namespace, you bring certain modules. One of them is the ng decorator that basically tells Python, you put it on a function and that tells to Python, I want to JIT compile this function. Then we have the OpenMP context because we create regions in OpenMP using with contexts in Python. So we try to be Pythonic. With context resource manager, they seem like a very good abstraction that you can use to create, OpenMP regions. And what we do is that inside the OpenMP context, we give as a string the same directive and the same clauses that you would give if you were writing a C++ Fortran program. So that kind of tries to build up on the experience of people that already use C++ and Fortran, and they would like to transition to Python or try Python and see if they can get good performance and high productivity. So we kind of try to play that set there and go for that string representation. And then this program, there's something very trivial. It prints like hello from thread, and that's how we showcase how we use like runtime functions. It's just another import. You import that function from the Numba OpenMP namespace, and then you can call it, and you're gonna get hello from thread, as many threads as you have in the monitor. So going a little bit more general, which is on the GPU programming, which is mostly what we're interested in here. This is kind of the general form of PyOMP GPU programming that we support right now. So it supports the common core, so it supports things like target, teams, distribute, parallel for, combined or nested. We support target data map, enter and exit if you want to create an environment, a data environment. We support mapping clauses. We support thread limit. So we support the common core of most of the things that people are using in PyOMP, and this is evolving, right? So we are adding more features. And That's a more complicated example. That's supposed to run on GPU. So it builds a little bit on what we talked in the previous slide. Again, we have the imports. In the imports, we bring stuff from the Numba OpenMP namespace to our program. And then here we showcase things a little bit differently. So basically, we have a target directive and a map. So we create a data environment to run on the device. And then we nest the loop this time. And we use the loop directive, which is shorthand for teams distribute parallel 4. And we also support reductions on the GPU, privatization. So that kind of tries to showcase like more features that we have now available and implemented on the GPU. You might as well put those things together, make it one combined directive, and you're not gonna need a map then. I mean, if you have a reduction, that's automatically gonna map, to from this variable. So apparently this program, calculates pi. It's not, terribly useful, but I think it shows like a lot of the nice features that we have implemented right now. And this is, the overview of how PyOMP works. This is what kind of extensions we had to do to the Numba compilation to be able to support OpenMP and CPU-GPU parallel programming. Most of the stuff that we did are the ones that are highlighted in green. Hope it shows well. So, up to that part, we're like, whatever Numba does already, okay, we have the OpenMP context and those get encoded inside the Numba IR. And that's where we start doing things. We take the Numba IR, we understand OpenMP through parsing. And basically then we do split compilation like most compilers do when you have to do heterogeneous compilation, compile for the CPU and the device. One part is the host, the other part is the device. And then we have an LLVM pass that's going to understand the LLVM IR that is going to be lowered from Numba, and it's going to create, the two different versions, the host and the device LLVM IR, including the OpenMP runtime calls. And we're going to have the device binary created at the device path and embedded to the host path so that it can be loaded and executed at runtime. So I went a little bit fast now, but I'm going to go like to each of those steps and explain it a little bit more in detail. But that's kind of the general architecture, split compilation, extensions to understand, extensions in the parser to be able to understand the OpenMP semantics, creating Numba PyOMP IR nodes, lowering them to intrinsics, and then passing those intrinsics through an LLVM pass that's going to create the LLVM IR plus OpenMP runtime calls for the host and for the device, and then the typical thing that you embed the device binary. So I'll go into a little bit more detail and show how that looks like. So let's say we have this very trivial program up there with just element-wise incrementing an array, an NumPy array. So when this is going to go in, basically at that point here, after this passes through our parser, this is going to put like marker NumPy nodes. It's going to put like a region start and a region end marker. And inside those markers, we basically store informations like directive and clauses as tags. And the region body is basically the body of the code that is supposed to be executing within this, with context parallel region. What's interesting there, we have directives here, we have clauses. One interesting thing is how we map the arrays, the NumPy arrays on the device. So we treat them like smart arrays. So we know how big they are, we know the shape, so we transfer the shape, we know the stride, so we transfer the stride, and we also know the data pointer, which actually holds the data, and we transfer the data pointer. And because we know that the array metadata are supposed to be immutable, we just do like a to transfer, whereas for the data, because we know it can change, we do a to from. So at that point, this is what exists here, the Numba IR plus PyOMP IR nodes, and then this lowers almost one-to-one to LLVM IR plus PyOMP intrinsics. And it's exactly the same code representation, a little bit lower. So it has still the region entry and region exit markers, but this time those are like LLVM intrinsics. And again, the directive and the clauses are represented as directive and qualifier operand bundles. So it's just similar representation, at a lower level. Then this representation in split compilation, it's going to go into the two different compilation paths. So one to the device, one to the host. And that's where our PyOMP LLVM path takes over. So that executes in the context of the compiler at the middle end. And what it does is that it's going to outline at the device side, it's going to outline the offload kernel. It's going to create the kernel entry point here, and then it's going to call the device runtime functions that are needed to implement execution. Like in that case of the example of the element-wise increment, we have the target init and target init calls, and the device function, of course, and then we also going to be calling like the other OpenMP runtime functions. I mean, for people that are familiar, it's the initializing the distribute static implementation, the for static, making sure that we execute all the threads in parallel with KMPC parallel. So it's all standard stuff. And now what's going to happen is that the device compilation at some point is going to create a binary, and then at that point we also want to embed it in the host LLVMIR. So what we do is that the host LLVMIR is going to wait until this binary is available, and that binary is going to come into the host LLVMIR, and it's going to put the binary itself inside the protocol that exists for storing a binary and then loading it and executing it later. So basically we have a bunch of global variables. Those global variables store the images and other entries. They also store mapping stuff that I'm not showing here. And then at the host LLVMIR, inside the main function, at some point we're going to have this the target teams mapper call of the OpenMP runtime at the host, which is going to load the module and launch the kernel. Yeah, and then at the end of this compilation, we basically get this binary here, the executable binary, and the executable binary has the host binary code. It also has the device binary image embedded in it. It has the right OpenMP calls. So when this executes, it's going to run the device. So we wanted to understand, what is the performance of our compilation, and we decided to experiment using the Checkbench benchmarks. So the Checkbench benchmarks, a lot of people mention them. It's a very nice collection of benchmarks. It has programs like from different domains, and they're implementing different programming models, OpenMP target, CUDA, cycle heap. So it's very nice and heterogeneous. And we said we're going to take, the OpenMP offload C++ version for those programs, and we're going to implement them in Python using PyOMP. And the hardware that we tested with, it's an NVIDIA i100 GPU, and the software environment is Python 3.9, CUDA 12.2, and Clang LLVM 14.06. This is the benchmarks that we tried. So we tried to pick things from different domains. So the Adam optimizer from ML, Floyd Warshall, I mean, you probably know them. And then the metrics that we wanted to contrast those two implementations, one was kernel execution time. We wanted to see what is the kernel execution time when we do the C++ version of OpenMP offload. What is the kernel execution time when we do the Python version of the code? And then we want to see, how much is the data transfer size, how much data to transfer in Python versus C++, especially since we know that smart arrays, they have the metadata, so we're always going to inflate that a little bit. The same thing for time. And then compilation time, we want to see how much time do we spend doing JIT compilation versus how much time like the ahead of time compilation takes to compile like the C++ OpenMP program. So all those metrics, the lower they are, the better. So they are all like lower, better metrics. So this is the first result. Kernel execution time. The big header is PyOMP is competitive with the C++ version, which was actually a very good result. And initially it was a little bit weird as well. Also, if you see the asterisks, which I'm going to explain. So on the left side, blue one is the OpenMP C++ version. On the right side, the orange one is the PyOMP version. And if you see, like in two of the benchmarks, we're very close. Adam, Lava, MD. One were worse in the HackMK benchmark, the kernels. And the reason for that, when we traced it, is that the Clang frontend actually optimizes for FMAs because of the way compilation works for the GPU. In our case, because we compiled from the Numba frontend, we didn't have this FMA optimization. That's why we were losing performance. Since then we added it, and basically we are on par in that case. Now, the more interesting cases are the ones where the Python implementation is faster, and in some cases a lot faster than the C++ version. And we traced that the problem was that toolchain differences when compiling to the GPU code down to the binary between the C++ Clang version and the Python version. Basically, the C++ version uses the NVIDIA toolchain and creates relocatable code, whether what we do with numbers that we use the NVIDIA interfaces through the API to compile that code to binary. So basically what we expect is that if somebody does LTO or with recent LVM upgrades, we expect performance to be on par. So it's just a toolchain difference. It's not that we generate, much better code. The other thing was data transfer sizes. So in that case, we look how many bytes do we transfer from the device to host or from the host to the device. Again, blue is C++ OpenMP, orange is PyOMP. And we wanted, what we expected as a result that we see in most of the plots is that we inflate a little bit the number, the size of data transferred because we're going to add metadata to arrays and all that stuff. So that's what we see most, except for LavaMD, and that was a little bit of a surprising result. And that happens at the host to device. And when we looked at the code, what happened in LavaMD is, if I recall correctly, there is a structure of arrays that gets transferred from the host to device. And all those array fields are actually not used on the GPU, but out of programmer convenience, they're all transferred with a mapping clause. When we did the same implementation in Python, we broke the structure into individual arrays, and we passed them up to the Python code. And the Python compiler was, the NumPy compiler was smart enough to understand that some of those arrays are not actually used and remove the code. So we got unexpected optimization through the Python compilation. So yeah, that transfer size is almost the same. But when we looked at the data transfer time, we saw that usually PyOMP is slower. There is, especially here in LavaMD from device to host, there was like a big jump between how much time we spend transferring data in PyOMP versus how much time the C++ version spends. And one of the reasons was that the metadata that we transfer now for the smart arrays, we basically transfer them as individual data transfers. So every metadata item is going to create one memory transfer. This has like static overhead, all those kinds of things. And it can be easily optimized, just that we need to improve our implementation. Basically, we need to coalesce all of them. The interesting thing is that in the host to device transfer for LavaMD here, we do see the reduction in time because of the optimization. So that was pretty cool. But yeah, more or less, we want to do optimizations like that. We want to coalesce memory transfers. We want to try to see if we can elide some of those memory transfers, especially if we know statically how big are our metadata. And that's something that we're working on. Now, the third thing is compilation time. So this is the ahead of time compilation time of the C++ program versus the just-in-time compilation for the same program. And I'm saying first time here because Namba caches your compilation. So once you compile a function, this is going to be cached at runtime, and it also allows you to cache this compilation also on disk, so you can reuse it later. So in that sense, we do have like inflated compilation time. This is expected. We are going through a Python path. We also haven't optimized, our compilation pipeline. We have like a lot of verification here and there to be able to understand if we make a mistake, where did we do it? So it is slower, but caching mitigates this slowness, and we can optimize and make it faster. So conclusion, we have PyOMP, which brings OpenMP GPU programming to Python. We implemented on top of Namba and LLVM, and we do have competitive performance versus C++ OpenMP. And thank you very much. This is my email, and this is the repo where we have like all the code. It's open source. We also like test very regularly. We test both on both on NVIDIA GPUs and on CPUs. We have like something like 200 tests that are running constantly. So it's pretty robust, and we welcome like user feedback. So if anybody of you uses it and you see a bug or you want a feature, we're open to discuss that. Thank you very much.
Thank you.